Hello everyone. Actually, during the chemistry class, with Professor Dimitri give us a class project, and I work on the. Sorry, what happened? How to remove this one? Okay. So I work on the computational simulation. Um, Computational simulation of the undoped and doped model of cis polyacetylene, and where we used different types of doping, p and n type doping, and we try to compute uh, we try to explain that using doping and p-type or n-type doping will give shows that material behaves like a conductive material. So the we use this one like um, here the outline of this research work, objective, then conclusion, introduction and model. I will describe the methods I used in this research work, and the background of this work, why we use this model, result, discussion, and conclusion. Okay, so the objective of this research is to understand the charge transfer process um, using the uh, P or N-type doping. Why I'm not able to see it? Professor, do you know? Okay, yeah, I already just one. Okay. Like to control the conductivity of the conjugated polymers by injecting charge or adding and injecting charge or adding doping. And also we try to prove that the doping and injection are shows the equivalent result, and it shows that the influence of the in doping and injecting, and after doping and injecting the charge, that material behaves like a conductive material. Okay, so this is the conclusion of my class project work. So there on that time, actually I add some doping in the model, and also try to injecting charge, and we can after injecting and charge and adding doping, and will give us that material behaves like a conductive material. After and also we after comparing all the result, we can say that after removing charge from the undoped model, that undoped model showed the less band gap compared to the others. So that means that material behaves like a more conductive material. And also we prove that I will show it later, that the injecting charge and adding dopamine have equivalent influence on the electronic properties. Their result more or less same. Okay, so the this one electrical conductivity. Actually, electrical conductivity is the property of a material that determines how well that material behaves like a conductive material. So, like um, the thing is, all kind of conductive materials, mm, they normally follows the Ohm's law. This one it's written here: I equal to U by R. So here I is the current throughout a resistor, and U is the drop in potential across that resistor. So the R resistance um, uh, it can be measured by applying known voltage across the resistor and measuring the current through it. So the electricity conductivity is that one is closely related to the resistivity, and not all materials obey Ohm's law. Mm, like few materials on few materials it's written on the literature review I read one in one papers that gas discharge vacuum tube, some semiconductor materials actually in those and few conductor materials, uh, those are follows this Ohm's law. uh, yes. Okay, so from this slide, we are able to see that there is a two figure. One when there is a huge gap between the conduction band and the valence band. It is that means that material behaves like isolator, and when there is compared to small band gap between the conduction band and the valence band, it that material behaves like a semiconductor material. And another when this conduction band and the valence band, they are overlap with each other, then that material behaves like a conductor materials. So the second figure, this one actually explain my models clearly. That's why I use this one. So here it shows that in conduction band and the conduction band, and there is a gap between conduction band and valence band, and that means it behaves like a semiconductor material. After that, when I remove electron from this conduction band, then LUMO is goes down, um, and it overlap with the valence band. And so according to the um, definition, it shows that if we remove electron from the um, model, it behaves like a conductive material. Again, when we like mm, we remove sorry um, and here if we remove add electron here in anionic state, it's add electron in this state, then that HOMO goes to the with the conduction band. So it also shows the conductivity of the material. So here actually few researchers they explain the conductivity of this material, and this paper actually written so many years ago. They used a single chain structure of the polyacetylene, and also they did this one in they experimentally showed that if they injecting doped material, they used potassium bromide, so that after injecting that material, that model polycetylene, that single chain, and shows the conductivity. So here from the figure 1, it shows that actually the figure 1 shows the absorption spectrum. um, Here absorption spectrum change of the thin polycetylene film, and they used 60 degrees Celsius. They used 60 degrees Celsius, and here we able to see the first peak at 1.7, and the second peak we are see that around 1.8. When they applied the heating, that polycetylene at 60 degrees Celsius, the broad band in the region, it's like uh, um, 1.5 becomes more intense, and the 1.8 wave, 1.8 into 10 to the power 4 wave number then becomes weaker. Like when temperature started to increase, it like this absorption spectrum showed some different values, and um, it's they actually try to prove that injecting doping materials, after injecting doping materials, they showed so the less band gap. And so less band gap means that material behaves like a conductive material. So here actually there are two types of polymer. One is with a uh, chain CH2 and another with CH bond. So first, at first, when I did the class project, I used the first one, uh, uh, and on that time I used uh, PB function method, and after that, professor actually suggested me that remove some electron, means hydrogen, from the model, and um, do the calculation and compare the result. Uh, and we were able to see that um, after removing electron from the model, that one gives a best result than the previous one. So, so here actually uh, um, uh, for this project, I plot density of state and absorption spectrum graph using this methods, like in the electronic structure of the atomic model. Actually, we determine by density functional theory, which is implemented by VASP software, and their atomic model is defined by initial position of Ri, and the atomic number Ne, that in electronic number of electron. And here we use the first equation, the equation 1. This is the main equation of the DFT function, and after that we compute the total density of the electron using the equation 2, and it, using that equation we will able to compute the total density of the that potential uh, function. So there this v which is determined as the functional derivative of the total energy in respect to the variation of the total density, which is include the interaction of the electron of ions, uh, and they have interaction like Coulomb interaction. It shows the correlation between the electron, and obviously there is exchange interaction as well. So equation 1 to 4 are solved in a iterative and self-consistent manner by using the vast software, and in according to use we used PBE function. PBE functional, we used that one. So there for the density of state, like for the density of a state, and that one actually describes the number of state per interval of energy. And here this one in the equation, um, with this one actually ds is a characterized electronic structure of this model. So DOS is actually defined by equation 7. So sorry, it's not 7, it's equation, this equation. uh, and where the direct delta function was approximate with the finite with a Gaussian function. And also there are another important parameter, that one is the that one is the oscillator strength, which is representing probability of that model which absorbs a photon will undergo an electronic transition. So this one Fij equal to this huge equation, that one actually used to compute the oscillator strength, where omega ij is the angular frequency, um, which is required to excite an electron from state I to state j, and dij that one is the which shows the transition dipole moment um, for transition from the state I to state j. And after that we compute the spectral density of the absorption using this one, sorry, using this one alpha omega. So there is a strong relationship between the absorption spectrum and the conductivity. They are closely related to each other. So generally the conductivity is like actually equivalent to the absorption of the conjugated polymer. So when that omega, that frequency will be 0, we expect that uh, at its 0 frequency, the absorption spectrum will be high, and we will able to see the fast absorption peak when the frequency will be 0. So like this one is so complicated. Like if we consider only single oligomer, it will be easily explained in a particle in a box. Uh, so and from that, like in the inside of particle in the box, their potential energy is zero, and the outside of the box, their potential energy is infinity. So normally, particle in a box can be explained for the single oligomer, but this one will not give us exact result. It's not give us accurate result. So that's why here we used several oligomers. We used the 6 oligomers here. Why we use the 6 oligomers? Because like when there will be the 6 oligomers or the 6 chain, that oligomers will be they are
May I interrupt?
yeah.
So here you are speaking about single oligomer, right? It's different
Yes.
electronic states of one on one oligomer. You are going
Yes.
to 6 oligomers later.
Okay. Okay.
Yeah. Okay, sorry to interrupt.
Okay. Okay. Uh, this one actually showed the inner orbital energy of the single oligomer. So we compute this one, and after uh, that we are able to explain that this one perfectly shows the uh, particle inbox, like this uh, uh, shapes means when oops, sorry. This one like when n equal to 1, uh, that one behaves shows the sine function, and when the number n equal to 2, it's sine function uh, uh, that envelope actually shows that two round, it's not round shape, that arc sign, that one I forgot the number, that arc sign. And after seeing the band gap of the single oligomer, we are able to see that there is like a it shows the larger band gap compared to the uh, our previous model. So it's better to use the like more oligomer rather than the single oligomer. Okay. Uh, so here actually we we this one for not the single oligomer. It's because we have the model, and we remove some electron atoms from that model, like this one, and the undoped model, and the from undoped model around 12 atoms removed from this the previous undoped model. Then after that we plot the absorption spectrum and graph, and we are able to see that. And actually it's I need to show the density of state graph, but there's something wrong with that. That's why I just show this one. So the undoped neutral has the valence uh, that valence band fielded, and that covalence sorry conductive band is empty. So there is transition of occurred from the occupied to unoccupied only, and that's why it called interband. So interband is like when the transition occurred between the electronic state with within the no, interband transition is like when the transition occurred between different bands. So here transition occurred from the unoccupied to occupied. So that's why we call it like interband. And if we look at the uh, doped model, and here we able to see that in the occupied orbital, there in the first section, there are one okay, one that blue line, it shows that it's that in unoccupied section there is also a unoccupied part. It's empty orbital there, we are able to see that one. So for that empty orbital, actually it will be show the two types of transition. It's one is intravent and another was is interband. So in intraband is like when transition occurred between the same band, within the same band, like here transition occurred uh, within the occupied state. Like in the occupied there is the a, that violet color, and there is another empty orbital there. So there for that unoccupied, uh, in the valence band there is empty orbital. So for that empty orbital there is uh, another type of transition occurred. So this one this actually slide 14 and slide 15 actually same. It shows the absorption uh, spectrum of the graph, and here it shows two type of transition. And after that, actually I need to do several calculations. Those are not done yet, and I need to complete that one. Maybe later I will show those things. So like during the class project, actually I used professor, one minute. So during the okay. So during the class project, we used three types of model. One is undoped, and this one is doped model, and co-doped. And the doped model here we inject p-type p-type dopamine and p-type here we use p and n, and two types dopamine here. So like um, why it's not working, not working. Professor Dimitri, I think you need to share this. It's okay. So after that so after that I plot density of state graph for all three models. And here I this the first row for the neutral state of the each model, and this one cationic, and after that this one anionic state. And so here for the undoped one, we are able to see that it shows the band gap around point four, around point 0.4 band gap. It shows that. But when we did calculation for the cationic state, it shows that the occupied and unoccupied orbital actually overlapped with each other. So and it shows the, if we are look at the table from that that one is cationic state, and this one NRE. So if we look at the band gap of the doped model, it also shows the less band gap. This one and this this one, their result compared to same, like after adding charge, and this one like just adding the material, doping material, it shows almost the same result. Okay. Okay, so this one this one actually I plot density of state. The previous one I plot density of state using PBE function, and after that we plot this one for hybrid function method. And using the hybrid function method, we are able to see the result and compare the result that it's a neutral state. All are neutral state. And this one, an HSE hybrid function method shows higher band gap compared to the PB function method. So this one shows the absorption spectrum graph, and at zero frequency, it shows the higher absorption spectrum, like this one, blue one. Okay, the cationic undoped, because its band gap was less than compared to the other materials. So that's why it when we compare all absorption spectrum together, we are able to see that at a zero frequency, the cation undoped spectrum shows the higher absorption. Like it's zero frequency, means absorption spectrum is high. Okay.
Can you
Yes.
yes? So let me make a comment and invite
Okay.
everyone to look at this slide and prepare questions, because this is the main slide of the presentation. And if there are questions about validity of approach or about the conclusions, it is something to focus at. So the rest are just supporting information, and this is strongest result where circles on the left uh, differ by several orders of magnitude in their height. Okay, just ask if there are questions, and if there are no, feel free to continue.
Do I
I
need
guess
to?
I just have one question.
Sorry.
So I guess the main question I would have is, how sensitive is this plot to like the change in the broadening parameter that's used to plot spectra? I guess you don't know that because you've only done it once, but that would be my main question, to see if whether these results still hold if you change the broadening parameter, whether like the trends stay the same.
Let me try to oh, okay, if you want, please do. Please answer.
Aaron maybe asked that if we change the frequency,
no,
then
broadening parameter, the width parameter, which one is using while computing spectra.
the result will be the same, I guess.
Yes and no. Let me contribute to discussion. The absolute values of the results are very sensitive to the broadening parameter. The relative, if one looks for heights of these circles in respect to each other, then their relative height will hold approximately the same. So the cyan circle will be like 3 orders of magnitude higher than purple anyway, even if you change the broadening parameter, but absolute values will be changed. And if one wants to be as close as possible to experiment, the width parameter should be selected based on the temperature, on the thermal broadening. But in order to better comparison, a researcher may just explore wider range of these broadening parameters. Does it answer your question?
Yep.
Okay, thank you.
Okay. So after computing the absorption spectrum, then we compute the absorbance wavelength, and so we are able to see that it's like when absorption, the wavelength is around 3000 nanometer. All model shows the higher absorbance, like it's uh, we can say that it's a reverse to the absorption spectrum graph. Like in the absorption spectrum, it shows higher value at zero frequency, but here it's shows higher value when the wavelength is more. So here we can see this blue line, this one. Uh, no, not this. So like undocked this one. Okay, sorry. So this one undocked model is at like this one shows the higher absorption, but I don't know why it shows this one. I did something wrong. So it seems like that when wavelength will be increased, absorbance of the material will be increased with that. So after computing the density of state, absorption spectrum, and absorbance, I plot the uh, charge density of each model. This one actually shows the HOMO -1 orbital. So this peak means in this peak, in this area, uh, this oligomer, like the third oligomer, uh, mm, is more chargely dense, more it shows more charge density rather than others. So that's why there is a peak inside, and in the in the edge of the box, there is less charge density, similar to the projection on the z direction. There is this one shows the highest peak. This, like this one, shows the highest peak because of the third oligomer, and like mm, the third oligomer is occupied with more charge density. So like compared to the this one, and if we look at the HOMO orbital, we are able to see the highest peak there. It one for the highest peak, that means that in that projection, like position in a z direction, this oligomer are more mostly charged, the most charge it shows most charge density rather than others. But like there, it shows um, highest peak in the middle, but in the homo orbital we are able to see the highest peak at the edge of the box. Okay. So like in the LUMO orbital, the LUMO orbital, it shows a high, similarly it shows a highest peak in the middle section and in the X and Z direction. And so that means that those are like the third oligomer. This highest peak because of the third oligomer is occupied with the charge density. And the LUMO +1, that one shows the highest peak at the edge of the box. So similar things I plot for the doped model and co-doped model as well, and there we are able to see that here we add materials. That's why there we are not able to see the highest peak. That oligomer not shows the charge more charge density. So it's like that doping material affect the charge density. That's why it shows peak in this area, like 1, 2, 3, in the third oligomer, and in the X, so this one X direction, and in the Z direction, it shows highest peak, the more charge density in the middle section. And similar things happened in the homo orbital as well, like doping actually affect the charge density. So that's why here in the Z projection on the Z axis, we are able to see uh, highest peak in the middle, and uh, there is highest peak, and that means some more charge density at the edge of the box in the X direction. So we plot actually same things for the LUMO and LUMO +1, and LUMO in the LUMO +1, this the fourth oligomer shows the high oligomer is occupied with more charge density. That's why it shows a highest peak in the X direction. We are able to see this one red line, and it shows highest peak in the middle of the box in the Z direction. Similar things happened in the LUMO +1 as well. Like it shows the highest charge density in the middle of the box in the Z and X both direction. Uh, So actually I plot charge density for each model, like doped, undoped, co-doped model, and after that I did molecular dynamic this calculation, and if we are able to see this band gap of the density of state, and I compare this density of state with the neutral state, it shows that after applying heat and calculating molecular dynamic, that one shows less band gap. That means like we if we just uh, did molecular apply heat and did molecular dynamic calculation, that material will behave more conductive materials than others. Okay, so this on the graph, main graph actually. Here I applied 1000 K to temperature, but I don't know why there is like after 3000 it shows like this. So I think I need to calculate this one again, and let's see what happened. This one actually I made video for after calculating those things. It, um, like this one doped model, like, oh no, okay. uh so as
Wait, wait,
I
wait,
said,
wait. Why don't you run the video?
which one should I run?
Just all of them, one after another.
Okay, okay. Oh, sure. I thought I don't need to run. Okay, let me. Why it's not? Just 1 minute. Okay. Yeah. This one, like after. Why it's okay? It's already. Um, so after applying 1000 K temperature and doing MD analysis, we are getting this kind of things for undoped. This one for the doped model, and this one for the co-doped model. Okay, so we already showed that adding doping and injecting charge uh, mm, uh, more or less showed the same result, and we already proved that one, like I showed the table before that one. And that means that adding doping and injecting charge uh, will accelerate the material to behave like a conductive material. And after those things actually done in the most of the things actually done in the class project. And now I'm focusing on the hybrid function methods. So only 2 calculation is done. Still 9 calculation left. I need to finish those one. And um, 1 day or 2 days ago, professor again told me that I need to do another calculation for the trim. We already trimmed the model, so I need to do the all calculation for the trim model as well. Then we will compare those results to see that which one gives a more accurate result. That's it.
Okay, please join me in thanking Kiev